let's try this question. You have two subspaces, U and V, and the question is already accepting that these U and V are subspaces, so you don't have to prove that these are subspaces. And the first question is to express U as a span of two vectors. Now, before even trying to solve this, let's think about what kind of space this is. It has two parameters, right? X and Y. So there are two directions you can go. Changing X will make you go in one direction. Changing Y will allow you to go in another direction, right? So what will be the dimension of this vector space? If two distinct directions, what's that? Yeah, this will be two-dimensional, right? So it's not a surprise that it can be written as a span of two vectors. Okay. Now, it turns out that as long as you can find two vectors that are pointing in different directions, you can always use those two directions to represent any other vector in here. Okay. So can you give me one example of a vector that belongs to U? Let's just try one. Let's say 1, 2, 2, 2. Is this in here? Why is that vector in here? Because you can set X as and Y as 2, right? So definitely this is in U. Okay, give me another vector that's in U. 0, 1, 1, 1? Okay, good. 0, 1, 1, 1. Now, are these pointing at the same direction? Well, if they're pointing at the same direction, then if you have two vectors pointing in the same direction, one is a multiple of the other, right? But this is no way this is not a multiple of the other, right? So definitely these are pointing into two different directions, and therefore, since you have a linear space, it must be that any other vector could be written as some linear combination of these two, right? So that means probably x, y, 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 any vector that belongs into U must look like that, right? And we should be able to find out A 1, 2, 2, 2 plus B 0, 1, 1, 1, where this represents this other one. If that's true, that means that U is going to be span of this and this. Because what is a span? Span is a collection of all the possible linear combinations, right? So that's what's going to happen. Now let's try to simplify this. What is this? This is A plus 0, comma 2A plus B, 2A plus B, 2A plus B. Okay. So for this to equal to this, A has to be X, right? See, you have X here, you have A here. The only way that these two could be equal is when A is X, right? Okay, and then 2A plus B must be? Oh no, this is a second component that has to be same as this one. Right? So 2A plus B must be Y, right? So that means what? That means B has to be Y minus 2A. Okay? And that means that any vector can be represented as X times 1, 2, 2, 2 plus Y minus 2A. Oh, but A is X, right? So you can rewrite this as Y minus 2X. So you can write 2X times 0, 1, 1, 1. And because these are real numbers, definitely this proves that this is in the span of 1, 2, 2, 2 and 0, 1, 1, 1. Now, furthermore, you still have to show that this see, I want to show that this is same as u, so you actually have to show the other inclusion as well. You have to show that if you take anything that's a linear combination of these two, like this one, and if you write like this, you have to show that this is in there. But that's kind of obvious if you set x as a and y as 2a plus b, then this is obviously in u. So you have to write the other inclusion. So that's one possible answer. In other words, the answer to this question is not unique. You have so many different options, okay? So I just wanted to point out that this is possible. Better one. Who can think of a better obvious one to choose? Well, obvious list to choose? For A, if you have x, y, 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 that's same as. Can you think of a choice of obvious vectors? Anyone?
Zeros.
Huh?
Zeros.
Now, if you have everything zeros, you can't represent this. This is not good.
0, 1, 1, 1.
Okay, you want. Okay, let's choose that as the second one. 0, 1, 1, 1. What's the other guy?
1, 0, 0, 0.
Yeah. And what's the coefficient? Right? That's right, right? Okay. So this obviously shows that this shows that u is equal to span of 1, 0, 0, 0 and 0, 1, 1, 1. And here it's rather direct. You know that this belongs here, right? But anything that's in here looks like this, and therefore it's same as that one, which is in U. So you can, just writing it this way shows that these two are equal. So inclusion in both directions is like automatic. That's why it's much better than the other choices. Okay? All right, so in the same way, how would you write V? V would be span of, give me two vectors.
1, 1, 0, 0.
And then?
0, 0, 1, 1.
0, 0, 1, 1. Okay. And again, because x, x, y, y is equal to x times 1, 1, 0, 0 plus y times 0, 0, 1, 1. Right? Okay, so these questions, if you see the answer, it's really simple. But if you don't know, then it's hard to think. But at the same time, having some understanding of the geometry is really helpful. See, this part is presented before we even spoke of basis. So we don't know what a dimension is. Those are later. And yet, in order to solve this, you have to have that constant. You have to have that understanding that, oh, this has two parameters in R4, so it's probably two-dimensional. That's also two-dimensional, right? And then, let's think about this one, U plus V. What will be the dimension of this guy? Well, would this generate all of R4? Let's see, if you have something like 1, 2, 2, 2, and you add something like 3, 3, 4, 4, that's like something in here, right? If you collect every vector that's a sum of something from here and something from there, how would it look? This is how it looks like, right? Is there a common feature of all the vectors that's made by adding these kind of vectors? Do you see a common feature here? 3, 1, 1, 1, right? Or -1, -1, 2, 2, something like this. And if you add, what do you get? You get 2, 0, 3, 3. That's another vector that belongs in u plus v, right? Do you see any common feature here?
Last two are the same.
The last two are the same, right? Yeah. You always have last two the same because this one has the property that the last two are the same. This one also has the property the last two are the same. Therefore, if you add them, you always have the last two the same. Okay? So does that mean u plus v gives you the entire R4? Yes or no? Can you think of a vector that does not belong to here but belongs to R4? Give me an example. Okay, you're not going to learn anything by just staring at what I'm trying to solve, okay? You're only going to learn by saying something, even if it's wrong, okay? So, say something. U plus v, does u plus v contain all the vectors in R4? Yes or no? If it's no, give me an example that belongs to R4 that does not belong to u plus v.
So the first two, x, y, and x, x.
No, don't give me general answers. I want a specific example, okay? Give me a specific example that does not belong here but that belongs there. Yes?
1, 2, 3, 4.
Yes, correct. 1, 2, 3, 4. Now, 1, 2, 3, 4, that's definitely in R4, right? Because you have 4 numbers, right? Why is this not in here? Because of the observation that we just made. For things in here must have the property that the last two has to be same. Okay? All right. So, because of that, we know that this must be at most what dimension? What's the dimension of this? At most.
R3.
And you can't say R3, no. Dimension 3. R3 is not the only vector space that's of dimension 3, okay? So you have some slanted dimension 3 vector space in R4, okay? So it could be dimension 3, or it could be 2, right? Or it could be, can it be 1? No, it can't be because this contains u and we already know that this is dimension 2. So we know that this is dimension 2 or 3. Okay. Now, none of this that we're talking about at this point should be written in the solution, in the proof. If you do that, that's going to earn you no points. Why? Because we haven't defined what basis is, we haven't defined what dimension is. Okay? Yeah. But we still want to talk about it because that gives you some intuition of what we are allowed to use and what we can't use, right? So this is definitely more than 2 or 3 dimensions, okay? But here it says hyperplane. Okay, apparently this question is giving you a hint. What's a hyperplane? Hyperplane is when you have a single linear equation equal to 0. Okay, that's a hyperplane. Okay. And such an object is dimension 3. You got that? It's dimension 3. Okay. And so it kind of makes sense. It's dimension 3. It's not all of R4. It satisfies one single equation. Because U is a span of 1, 0, 0, 0 and 0, 1, 1, 1, and V is a span of 1, 1, 0, 0 and 0, 0, 1, 1. That means U plus V contains what vectors? Give me the vectors that are in U plus V. Give me examples of vectors that are in U plus V. Well, what is U plus V? It's a collection of all the vectors that look like U plus V, where U is from U and V is from V, right? So you just have to find something in here, plus another vector in here, add them up, and you have to find another one here, and here, you just keep adding them. But the catch is, you want to find the simplest ones. Okay, so give me a very simple vector that belongs in U plus V. Can you do that?
2, 1, 0, 0.
2, 1, 0, 0. Okay, how do you get that?
Well, it's U plus V, so I can't.
You just added these two, right?
Yes.
I know this is from U and that's from V, so 2, 1, 0, 0 is in U plus V. Very good, okay? So that's the start. Give me another one.
0, 1, 2, 2.
That's true too, right? You can add these two, right? Okay. Now, can you give me even simpler one than that? Give me something that's like even simpler than those two answers that you gave me. Huh?
0, 0, 0, 0.
0, 0, 0, 0. Very good. That's definitely in here because any subspace will have it, right? Okay, good. Give me another one. Zeros. Okay, I guess that's the better way to say it. Can you give me a vector that's in here that has 3 zeros?
1, 0, 0, 0.
Yes. How do you get that?
Out of the Stony.
Because this is in here, right? But then 0 is in V, right?
Yes.
So if you do this plus 0, you get this in here, right?
Yes.
Okay. So my point is this. This U plus V is going to have every vector that spans them, right? So you're going to have 1, 0, 0, 0, 0, 1, 1, 1, and then 1, 1, 0, 0, 0, 0, 1, 1. All of these would be in U plus V. You agree?
Yes.
Okay. Which means the span of these guys also belongs in here. Okay. Moreover, since each one of these are spanned by these guys, right? I know that they're equal. Because by definition, everything in here is a linear combination of these two. Everything in here is a linear combination of these two, right? So everything in here is a sum of a linear combination of these two guys and sum of a linear combination of these two guys. So that's what it means by definition, right? Okay. Now the question is, are these linearly independent? What do you think? Well, we already know that these are linearly independent. It's obviously true, right? If you set something times this plus something times this equals to 0, then definitely you're forced to have x as 0 and y as 0. That's kind of easy. Now, what about this one? Is this linearly independent from here? I think so. Yeah. So, I want to claim one zero 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 0 1 1 1 and 1 1 0 0 are linearly independent. Let's look at that. Well, write down what it means. To show linear independence, you have to show that if there is a linear combination of these three vectors that's equal to 0, then you're forced to have all of these equal to 0, right? So let's see. This is, if you simplify, this is a plus c, and then there's no a anymore. It's b plus c, and then that's it. It's just bb equal to 0, 0, 0, 0. Okay? So this immediately shows that b has to equal to 0 because that's the third component, right? Now if b is 0, then you also have a plus c equal to 0 and b plus c equals to 0. Well, c is equal to negative b, so it's also 0. And then a is equal to negative c, but c is 0, so that's also 0. So we got all of them as 0, right? So this shows that it's true, okay? So it's proved. The proof of the claim is done, okay? Then now let's try to add this fourth vector. Is this linearly independent from the other guys? What do you think? Yes, that's what it is, right? So indeed, this is linearly dependent on here. In other words, this is in the span of these other guys because we know that 0, 0, 1, 1 is 1, 0, 0, 0 plus 0, 1, 1, 1 plus negative 1 times 1, 1, 0, 0. Right? So 1 times this vector, 1 times this other vector, plus negative 1 times this vector gives you 0, 0, 1, 1. Which gives you that this belongs to the span of just these three. Okay? So what did the linear dependence lemma say? If something is linearly dependent and it's in the span, then you can delete this, and this is same as the span of just these three objects, right? So the linear dependence lemma says the following. That u plus v is now same as span of just three objects, which is 1, 0, 0, 0, 0, 1, 1, 1, and then 0, 0, 1, 1. Okay? In other words, this is same as A is a collection of A times 1, 0, 0, 0 plus B times 0, 1, 1, 1 plus C times 0, 0, 1, 1. Okay, so A, B, C are real numbers. So that this is really collecting A, B, 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 and then C, C. So it's B plus C, B plus C. Okay, so if I have x equals to A and y equals to B, and then z equals to B plus C, and w equals to also B plus C, what's the equation that you get? So let's think about some equations you can get. You get these two the same, right? That's the observation that we already made, right? So z is indeed equal to w. But then for x and y, we can't say anything because a and b could be any number. So x and y are free to become any number. And c could be any number, so z and w, as long as they are the same, you can create this to be any number you want. Is that okay? Yeah. So, in other words, this shows that u plus v is a collection of any vector in R4 that satisfies this equation, z equal to w. And that is indeed a hyperplane, right? Because this can be written as what? 0 times x plus 0 times y plus 1 times z plus negative 1 times w equals to 0, right? All right? And then you have, so that's the answer. So the answer is that you have x, y, z, w, where x, you can just say z equals to w. Because this is indeed in this form. Okay? So it's a hyperplane.